Good morning, dear children. So yesterday we have started the pneumatic conveying. So let us have the recap of pneumatic conveying, and then that will be the end of second unit. Then we'll go to third unit. So in the pneumatic conveying, what happens is that we are going to transfer the materials from one point to another point in a closed systems by using an inert gas. When we say inert gas, the first preference goes to air because it is available everywhere, so that our operating cost decreases. Suppose if the product is sensitive to air, then of course there is no other go. We are supposed to use nitrogen. So when we use nitrogen, care must be taken to reduce the cost of operation by recycling the nitrogen. When you are using air also, care should be taken that the moisture content of the air will be reduced, and then that can be put for use, because you will see in chemical technology too that air containing moisture will trigger a process called as corrosion. So hence the air should be free from the moisture content, and then we can use it for this transportation purpose. So this is the flow sheet. It's a very important flow sheet. We'll have a quick revision of it. So roots blower. So in the fluid mechanics we have seen three types of devices: fans, blowers and compressors. Fans will be delivering large quantities, large volumes of air with a negligible increase in the pressure drop, or velocity will be less, but the volume will be more. But when you come to the compressor, the volume will be very less, but the pressure will be very high. So as you open it through a porous plug, a jet of gas goes out. So in between compressor and fan is the blower, which will be blowing the materials with a considerable increase in pressure, and then volume will also, to a certain extent, it lies between pump and compressor. Okay. So here the blowers are used. Roots blower is the name of an equipment. Where in fluid mechanics we are using low bay blower. The modified version of low bay blower is roots blower. So this roots blower will be blowing the material, the air, which is used for conveying. Whether it can be air or whether it can be nitrogen, that we are supposed to decide it first. And that will be used for blowing. So it will be blowing through this pipeline. And to this pipeline we connect the feed. Okay, so by Venturi effect, what will happen? The feed whichever is present here by the hopper, by means of a feeder, this is a feeder, so it will be continuously admitting the materials to other side. Okay, so from here, from the gravity it will fall. So as they are falling, they are entering a jet. So instantaneously the solids which are falling, okay, into this line, they will gain momentum because of this jet which is moving, and they will also start moving. And when they are moving, they move along with the air. So hence here the name is material plus air. So this material plus air will go to a certain distance. So this point may be the inception point in the production block, or the godown, or the warehouse, or the tank farm, and this may be your place where the reactors are present. Okay, so there is a large gap between this point and then the delivery point. Okay, so that is important. So now this is sent to the diverter. What is the diverter? Yesterday I told, we have a pipeline in which we keep a segmented baffle, or simply take a plate and then whose diameter is the internal diameter of the pipeline, and the length is of course the pipeline. So you keep it in between so that you cut the pipeline to two halves. So hence the feed whichever is coming, that will be going into two sides. Okay, one part will be going to this side, another part will be going to this side. So this feed consisting of the gas and the solids, they come from here, and immediately we keep a cyclone separator. So a cyclone separator is a device which is used to separate solids from a gas on a continuous basis. So you do not stop the process. So hence, on a continuous basis, the feed will be coming from here, and tangentially we admit it. So this diagram we see in our 4th unit. So it enters this cyclone separator and then start rotating. As it starts rotating, what will happen? The material and the air will be thrown out. So the solids will be the first one to go out away from the center because they are in a rotating field. So since the solids are having some amount of mass, so they will try to go and stay near the adjacent of the wall. And since wall is not moving, and then the solids are moving, there will be a friction with the air, and because of it, the velocity of the solid will decrease, and by gravity they fall down. So the gas is sucked from the top, and that is taken out. And these solids now fall into the silo. So this is the feed hopper, this is the silo. So this may be at a far away place, and this may be in our production block. So in the silo, the solids will be stored, and in a controlled manner, they fall into the conveyor belt, and these conveyor belt will be charging the materials to the weighing hopper, where from there the activity or the processing of these solids will take place. So other part whichever is coming, that will go to the second cyclone separator, and from there silo, and the same process will continue. So the gas which is rising from here, now that is sent to the fabric filter. So if you have a Eureka Forbes vacuum cleaner, so it is nothing but a fabric filter. The pure form of fabric filter is Eureka Forbes vacuum cleaner. So in the fabric filter, of course, the fabric, what happens, the mass will be entering, air will be entering, and then through the fabric, the gas will enter, but the solids cannot enter, so the solids will be staying back. And hence the name of fabric filter is there. So from the top, the air or the operating fluid will be going out. So depending upon the importance, we can recycle it back. Okay. So this is about the dilute phase pneumatic conveying system. So here when we say dilute, we have another concept called as dense phase. They both differ in the concentration of the solids. So here you have material and air is enough. So depending upon the concentration of the solids, we have whether we can have a dilute phase or a dense phase. That is the only difference between two processes. Then there are two types of transportation systems are there, conveying systems. The first one is dilute phase and the dense phase. The process is same, but in the dilute phase, the population of the solids will be less. And in the dense phase, the population of the solid is number of solids in a given volume is more in case of a dense phase. The number of solid particles in a given volume is less in the dilute phase. That is the only difference between both the cases. Now, dilute phase conveying systems. Dilute phase conveying system means suspension flow where the conveying gas, usually air, is pumped through a conveying pipe at relatively low pressures and high velocities. Pressures are low, but velocities are very high. Why? Because our aim is to exert drag force on the solid particles. So when we wanted to exert higher amount of drag force on the particles, the fluid should have higher velocity. A fluid which is moving will have a higher velocity. So hence the velocity should be very high, so that these solid particles will be carried away along with the air. Now in our flow sheet, where this is occurring at this particular point. Okay, at this particular point it is occurring, where here the gas will be moving with high velocities and it is going out. But a pipeline is brought and injected into this one. So what will happen, as soon as the solids fall into this pipeline, now they are introduced to a moving fluid. So hence, because of momentum transfer, the solids will also have some amount of, solids will also gain momentum, and they start also moving this and from it. So thus they are suspended in this air and they start moving. The material loading factor, it is a big question. What is the material loading factor? The weight ratio of the materials to the air. So here, how much amount of solids you are introducing per air. Okay, suppose you are sending 10 kgs of air, you are taking 1 kg of the solids. So the loading factor will be 1/10. Similarly, if you are using 25 kgs for 100 kgs, so 25 by 100, 25 is the solids which you are sending into the system, and 100 kgs is the air which is moving. So this is the meaning of loading factor. So the loading factor will tell us whether the material, whether the system is a dilute phase or a dense phase system. Okay. Is the material loading factor weight ratio of the material to the air. So how much amount of solids we are transporting, or how much amount of solids we are going to use transport, how much amount of air is required for this is called as a material loading factor. Is generally in the range of 10 to 15 at the higher ends, and 10 to 15 kgs of material per kg of air. That is the meaning of it. So if you are using 10 kgs, 1 kg of air is used. 15 kgs, 1 kg. So this range is different. That will be different. But denominator is always 1 kg. Numerator is how much you are transporting the solids is important. Then what is the dense phase? The same flow sheet is used. The material is moved in a conveying pipeline to the destination in a non-suspension flow in a full pipe cross section. So here you see the difference. Here you have a suspension. What do you mean of suspension, sir? The solids are suspended in a gas, means what? The concentration of the solids is less, and the gas is lifting all the solid particles, no doubt about it. It will be taking it. But suppose if you have a non-suspension, means what, sir? You are completely transferring the solids as a bulk, and you are inserting some pressures over them by means of high moving gas. So in a higher concentration, this will be happen. So in a simple language, the population is less in case of a dilute phase. The population will be more in case of a dense phase. And the flow is full pipeline which will be going out. The pressures required are very high. So here the roots blower has to do more amount of work. The material loading considerably greater than going up to 200. So you can imagine 200 kgs of solids are transferred by consuming 1 kg of air. So whereas in the previous case, dilute phase, if you see, it is only 10 to 15 kgs. So 10 to 15 kgs of solid materials are transferred for 1 kg of air. Whereas in the dense phase, it is 200. So hence, just now I said, it all depends upon the population. So when the population is more, definitely the fluid has to do more amount of work in transporting the materials. Dense phase conveying is essentially in a batch process. So we are going to give a blast of air and then stop it, blast of air and then try and stop it. And then robotic equipment, because the pipeline which is used for the conveying, it should be able to, this pipeline I'm talking about, this pipeline, its diameter should be very high, because it has to hold materials which are having high energy. So pressure accepted by these solids, and then the fluid will be very high. So hence thickness is more. Because the thickness of the pipeline is more, he has used about robotic equipment. Then the specifications of the valves and actuators etc. should be considered cyclic nature of the operation. Suppose if you are using instrumentation process control, then of course here we will have a cyclic valve. Already we have seen in chemical technology one, what are the cyclic valves? Periodically they open in this direction. After a certain amount of the cycle, they will be opening in this side. So they will have one inlet, they will have 2 outlets. In the first phase, the gas will be made to pass through this. In the second cycle, that will be passed through. So this has to be done by means of a machine. That is, the name is called as actuators, which promote the motion inside the valves. Then valve, specification of the valve, that is 2-side valves, outlet. Then key components of these are what? Centrifugal blowers, twin lobe blowers, that is the other names of the lobe blowers. Okay, and then the pipeline is important, pipe structure, because the entire transportation of the solids is taking place inside the closed conduits, and hence we have a pipeline. And material pickup and feeding devices. So how we are going to see in this line, in this flow sheet, we have shown a small line here. Okay, but this is actually a Venturi connector. So you know, in the Venturi emitter, what happens when the fluid is passing in a direction in which the cross-section area is decreasing. We have studied this. So what will happen? The velocity increases, pressure decreases. So when the velocity increases, what will happen? It can try to push the materials with a greater energy. That's what is needed for me. The fluid has to do some amount of work. What work it is doing? It has to push, it has to exert some higher drag force. second. What is this? Yeah. Yeah. So here you see just one line is shown here, but this is actually built in a Venturi type of equipment will be there, where its main function is it will try to increase the velocity of the stream. When it increases the velocity, what will happen? At the throat we introduce this one. Okay, so when you introduce this pipeline, what will happen? Since this fluid is moving with a high velocity, it creates a vacuum and then it sucks the material into the system, and thus the transportation takes place. This is what he is talking about has the loaders. Yeah. Material pickup and feeding devices. What are feeding devices? How the materials are sent to the silos, etc. That is the diverters. Then air material separating equipments. Air material separating equipments. If you see here, air and material is mixed together, but where they are separated, that is in the cyclone separator, they are separated. So in the cyclone separator, what is happening? The feed consisting of air and the solids, they are separated. Solids are coming down, whereas air is going from the top. Okay, this is one point, one equipment, one component. Then the gravity receivers. This part is the gravity receiver. This part is which falls from the bottom. Then cyclone separator, the entire setup. Back filters. After the cyclone separators, we are going to keep a back filters to ensure that the solids are not at all completely cleaned from the gas before they are let out to the next one. Then material diverters, we have seen that the pipeline which is having a segmented baffle divides the feed into two fractions. So these are some of the key components which will make this pneumatic conveying system. So this is the end of the unit 2. So now, without wasting much of our time, we'll start our third unit. Third unit is a very big unit. It takes so many classes for me. Yeah. Now this is about size reduction. If you remember the finished process, that is pyrites process, we have started it with by means of pulverizer. So the ores are coming in the form of lumps, and now they are supposed to be, their size has to be reduced to minus 200 mesh. So there we have used a single equipment called as pulverizers, but in reality there will be n number of equipments will be used for the transportation of materials. Sorry, n number of materials will be used for size reduction equipments. So what are there and what is their hierarchy, everything we study in this. Similarly, which type of machine has to be purchased, because remember already I told one example, a person may approach us, he may be having some ores. So he will be approaching you to say that I wanted to completely convert these ores to this many powders. Then of course you are supposed to select an equipment for him. So equipment selection also depends in this particular third unit. Which type of equipment you are going to use, because we will see afterwards that solids are broken in different ways. 4 ways are there. So what type of forces are required for this kind of material. So we should know what is the strength of the material also, and how fast it can break by consuming less amount of force. For this purpose, what is the machines which are available for us, and how many types of machines I am supposed to use for reducing the size from a coarser size to very small sizes. So all this data we know here. Similarly, we have some laws. Okay, so Crittinger's law, Hicks law, Bond's law, which will be used for predicting the power consumption by the machine. So because we have to keep not only the product quality, but also we are supposed to choose a machine which will consume less amount of power, isn't it? So we are supposed to estimate theoretically how much amount of power is required. Then we should conduct an experiment, and then we should see what is the power consumed there, and we have to compare this, and then we have to give the best estimation to the customer who came to us for a particular activity. So all this data is understood, studied in this size reduction equipment, where we see some size reduction equipment. You are supposed to draw those diagrams in the examination. You are supposed to explain their functioning. There are some problems are there in power estimations. At least we have 10 problems in this. There are 2 proofs are there, and some amount of theory part is there. So this will be the time consuming unit for our mechanical unit operations. So with this note, in this unit we are exclusively studying what are the size reduction equipments which are available to us. So how it is possible for us to get powders, okay? Because pharmaceutical industry will be asking, can you give me minus 200 mesh particles, minus 300 mesh, minus 400 mesh. Their demand is increasing day by day, because you know very well, as the size of the particle decreases, its capacity to do work will increase, okay? And thus what will happen, the tablet will be dissolved fast, and then its activity will be taking place. So because we have to give tablets to the patients, and immediately the action of the tablet should take place. For this, the dissolution is very important. Keeping this as a field, you cannot give powders to, because we are supposed to see where that material has to be gone, and then the process of absorption in the blood, etc. That is a different story. But pharmaceutical industry continuously asks us what can be the preferable sizes which you can give to us. That is what they are going to ask. So let us see what are the equipments which are involved in this. But before that, let us see some amount of the theory part of it. Yes. The term size reduction is, yeah, thank you. The term size reduction is applied to all the ways in which the particles of the solids are cut, broken into small pieces. Size reduction is a unit operation in which the size of the particles are reduced. Suppose if somebody is giving us coarser particles. What are coarser particles? Coarser particles are those particles whose sizes are measured in inches or in millimeters. Now you reduce their size and then you give them mesh numbers, minus 200 mesh. You can give them nanometers. You can give them millimeter square per gram. So these are the variations of the sizes when you are going from coarser size to ultrafine particles. So hence this is called as size reduction, where particles are broken. How they are broken? We can also cut them. So remember, each and every particle is cut. So is it really possible for us to think of an equipment which will cut in, like our scissors? Yes, we have an equipment called as rotary knife cutter, which will be cutting the particles into small pieces. That we see in the equipment. And similarly, the particles are broken. Unless until the particles are broken, their sizes cannot be decreased. This is the concept. Throughout the process, industries solids are reduced by different methods for different purpose. For example, take cement, clinker is found. You are supposed to reduce it to minus 200 mesh. Pyrates are there, minus 200 mesh. But in the same process, if you see the roasting of FES, it is granulated, means what? We cannot reduce the size beyond a certain limit, because it requires fluidization, and fluidization requires amount of characteristics building inside the system. So there we should have one type of size. So to what extent the size has to be crushed is decided by the process and the design. Chunks of crude ores are crushed to workable sizes. What is the meaning of workable sizes? Because see, the transportation of big lumps is not at all possible. I said in the synchronity columns we will have ores, but the ores in a big lump, it is not possible. Please imagine from physics point of view, if you are transporting a big stone in a tipper, what will happen? So at the curve, the center of gravity will be destroyed, and immediately the truck will collapse. So in order to avoid that, what we do is we will convert that big lump into a workable sizes so that it will be uniformly distributed in the tipper, and then the mass, since it is uniform, the force exerted by it will be same. So then transportation will be easy for it. So that is the reason why at the ores only we try to produce workable sizes. That is important. Okay. So that is the meaning of workable size, means what? For the pack, for the transportation to some other system where they will go for different types of size reduction equipments. Or in your factory only you can have this, no doubt. But what is the first sizes is workable size. This is the meaning of it. Synthetic chemicals are ground into grinding process is ground. Synthetic chemicals are ground into powders. Sheets of plastics are cut into tin cubes and diamonds in our, because here you have seen cut. So sheets we can cut it. So similarly leather products we can cut it. Commercial products must often meet stringent specifications regarding the size and sometimes the shape of the particles they contain. So this is what the consumer demand. Imagine a situation that cement is not given in -200 mesh, it is given in 1 centimeter. So what will happen? What will happen is important. So it is not used for the purpose at all. So unless and until its size is reduced to small sizes, then it can mix and then it can induce the bonding properties in the feed. But if the lumps are there, it is in the very less. So hence the material fails. So it all depends upon the consumer, and consumer will purchase only commercial products. So hence commercial products size requirements are stringent, means what? Strict we are supposed to follow. So once they say -200 mesh, you can go for -200 mesh, and in some cases beyond that is accepted. But stringent means what? -200 is a must. And at the same time, what is the shape of the particles is also very important. So as long as you try to crush the size of the particles, definitely you will be having rounded particles only, not intricate shapes. Okay. Reducing the particle size also increases the reactivity of the solids. This is very important. What is the meaning of reactivity? If the solids are used for a purpose of reaction, then what will happen? Definitely, if the size is less, what will happen? Within a short span of time, the entire solids will be consumed by the material, by the gas or by the liquid, whatever is it, and then the reaction triggers. For example, you take sodium and then methanol. So sodium is a metal and methanol is a liquid. You add sodium into the methanol, what will happen? Sodium will dissolve first. It should dissolve first, and then in the liquid phase of the methanol, the reaction takes place. Now remember, suppose if you are putting lumps of sodium, what will happen? These lumps of sodium will take some amount of time for dissolution to take place. It takes some amount of time. Then afterwards, once we ensure that the entire sodium is dissolved into the methanol, then only we can ensure a reaction is triggering. So how do you reduce the time taken for dissolution? Reduce the size of the solid of the particles. That is important. But remember, this statement is not true for all the cases, because we should see the nature of the material. Sodium you start hitting, what will happen? The hammer and our hand will go some other place because it is highly reactive. So first step is what? Pertinent properties are very important. If it is not so reactive, then only we will try to crush it, and then you see the dissolution will take place. That is important. But what is the logic here? In case of a solid gas, solid liquid reaction systems, as far as possible, if you try to crush the solids and then put into the system, then definitely within a short span of time you get your product. This already we have seen in our finished process, where the pyrites ore were crushed to -200 mesh, and then they were dropped into the gases, and then the process of reduction took place. So the reducing the particle size also increases the reactivity of the solids. Next, it permits separation of unwanted ingredients by mechanical methods. Very good. So suppose if you have an ore and then you take FeS2, because we are very familiar with it. FeS2 is having SiO2 as an impurity. So how to separate it? Yes, if the concentration is less, you can use fluxing agent inside the reactor to remove it. But if the percentage is more, what will happen? We are supposed to go for flow flotation. So what is flow flotation? It is a process of separating SiO2 from the FeS2. So how it is possible? You are supposed to crush the ore properly. Then only the two chemicals called as SiO2 and FeS2 will come to the system. and now you use an air and oleic acid as a detergent, then we can separate them. So if you are having a bigger size of material, in the bigger size of material there is a variation of two chemicals will be there. So you try to reduce in such a manner that the variation will be minimum. It is possible only when you try to reduce the size of particle. So when you try to reduce the size of the particles, definitely we can have part A particle, part B particle, and then we can separate them, and then it can be further dealt with, whatever the process is there. Similarly, you take the case of separation of ferrous materials and non-ferrous, magnetic materials and non-magnetic materials. Crush them properly, and then as the powders are falling onto the bed, you keep a magnet at the driven pulley. Then what will happen? All the magnetic materials will be attracted to it. Non-magnetic materials are thrown up. Imagine you are keeping a lump. So what will happen? Lump will be attracted because lump will be having magnetic material and non-magnetic material also. And by default, what will happen? The magnetic material will be attracted to it, and since it is in the same mass, even the non-magnetic material also comes out. So we cannot ensure proper separation there. So hence, for a proper separation of materials or the ores, crushing is very important. And as far as possible, if we try to crush into minimum sizes, then we can perfectly go for the separation into two parts. Then it reduces bulk fibers for easy handling and for waste disposal. So if the fibrous materials are there, they occupy a lot of fibers. Fibers are characterized by means of length. So if it is size is reduced, then it is easy for us to dispose them or treat them or use them for further purpose. Then solids may be broken in many ways. So here in the first statement is said solids are broken, were cut and then broken. Very good. But now you say they are broken into so many ways. Now let us see what are those ways. First one, but only 4 of them are commonly used in size reduction machines. So the size reduction machines whichever we are designing, they will be using these kind of 4 forces for reducing the size of the particles. That is very important. So what is the first one? Compression. Second one is impact. Third one is attrition or rubbing. Fourth one is cutting. So in our chemical technology, whatever the machines we are seeing, they will be using one of the force which is given in the top 4 one. First one is compression. You catch a particle and then apply the force on it. You apply the force in such a manner the particle does not move. Then only when the particle, when you immobilize it, when you try to apply force on it, then only it will accept the force on it, and then a limit will be there beyond which if you apply the force, the particle breaks into pieces. The first step is what? We are supposed to immobilize the particle. Immobilizing the particle is called as nipping in our chemical technology. Okay, if you nip a particle in part, you are firmly catching a particle and then you are applying the force on it. Okay, so when you are doing some work on a bench wise, what will happen? You try to tighten the screw so that the bench wise firmly fixes the material, and then you can work on it. You can file it, you can create threads, whatever you can do like that. First step is what we are supposed, the machine should try to nip the particle first, and then after nipping, then it will apply the force. If it is not nipping, what will happen? There is a chance that the particle may fly off, and then the applied force may go as futile or useless, and energy consumption increases. So hence, the first method of crushing a particle is by applying compressive forces. The second one is impact. The difference between compression and then the impact is what? First we catch a particle and then we apply forces on it. We try to apply the forces on the opposite side. So what will happen? Compression will take place. Suppose if you try to pull them, what will happen? It is under tensile forces. The best example of compressive force is what? A brick which is there in your wall. So in your house you are having walls, in between you have some bricks, isn't it? So bricks are subjected for compression. So this is the force. Very good. Then what is impact? Impact is also compression, but application of huge amount of force on a specimen for a shorter duration is called as impact. Once again, application of larger amount of compressive force on a particle for a shorter duration of time is called as impact. Generally, impact is there by hammer. So with the help of hammer, you raise your hands, go to the larger extent, and then you apply it on a particle for a short duration. It breaks into pieces. Okay, that is the second one. And the third one is attrition or rubbing. So when we are dealing with the hardest material, compression and then compression and impact will not work. So hence what we are supposed to do is we are supposed to use shear forces on the surface. So the checky which is there in your house, if your house is having a checky Tiragali, or say for example, okay, the scissors is a different example. So checky is the best example. The checky, what will happen? The bottom foot is not rotating, but the top one is rotating Tiragali. Okay. So hence what will happen when you introduce the grains? What will happen? The shear forces will be there on the surface of the particle, and thus the size reduction takes place. Okay. So this is one example of attrition or rubbing, and the last one is of course the cutting. So we have, imagine a situation, a tailor will be cutting your cloth into the desired size, and then after stitching he makes a shirt for you. So like that, here also we have cutters which will cut the particles depending upon our desired sizes. So these are the 4 ways by which the solids are broken. The first one is compression, second one is impact, third one is attrition or rubbing, and the final one is cutting. By these methods of applying the forces on the object, the size reduction will take place. So all the equipments which will be there discussed from now onwards, they will be either using compression or impact or shear forces, cutting, or a combination of 1 or 2 forces. Let us study them when they come into the situation. Then a nutcracker or a hammer or a file or a pair of shears exemplify these 4 actions or this is. So these are some of the major simple things which we try to understand in our house. I think nowadays nutcrackers are not there because nutcracker ante ఒక్కపొడిని కట్ చేసుకునేటువంటి పరికరం. So now it is not possible. So when this book was written, they were still using this. But I know hammer is there. We know file is also there. So hand nails, after cutting the nails, you may have files, and we apply the shear force and take it. And then pair of shear, that is the scissors, are examples. Okay. So these 4 common examples he has given to us, which are domestically available. Based on that, we can derive the forces. Sometimes the size reduction results from attrition of particle by 1 or more particles or more intense shear in supporting fluid. So this logic is very important. Sometimes what happens, for example, I said nanoparticles. Imagine how can we create nanoparticles by mechanical operations? Is it possible really? Have you put a question to yourself? How it is possible for creating nanoparticles? In YouTube, we have so many videos. Sorry. Silver is used for purification of waters, and because of it, the cost of silver has increased tremendously. But silver is not used as it is used as a nanoparticle. So the point is how we can create the size. Is it possible for us to have a hammer for this? Imagine you keep something on a, say, a workable table in your workshop, and then keep a nut on it, and then with the help of a hammer you hit it. But definitely there is a gap is there between your hammer and then the workable table in millimeters, 1 by 10, 1 by 100, but the gap exists. But nanoparticles are less than this. How it is possible? Yes, if you see the YouTube, there are so many videos are there. During the reaction only it is possible for us to, reaction mechanism only it is possible for us to create the sizes of it. Especially I am talking about silver. Okay? Because I have seen the video, I am telling you. But as I said just now, pharmaceutical industry will be behind us. Give me the size of a particle which is less. Give me the size of a particle which is less. So how it is possible? Because even if you bring 2 hammers together also, we cannot create nanoparticles. Try to understand it. Then what is the science which is left out? That is only attrition. So what we do is, we will suspend a high stream fluid, and then we introduce these solid particles aligned. So when these solid particles are introduced into the high moving fluid, what will happen? They try to push each other, pull each other on the surface of the metal, and by among themselves, interparticulate attrition, the size reduction decreases. So what I want to convey here is, it is easy for us to reduce the size of 1 centimeter to 1 millimeter. It is very easy. Power consumption is also less. Okay, efficiency is also very high. But when you are going from 1 by 100th millimeter to nanoparticles, we have to consume lot of energy and efficiencies are falling. That is what I am going to say. And that we will see in our equipment. Don't bother about it. But since he gave one example how to reduce the size of the particles to very small sizes, I am discussing this. Some size reduction results from the attrition of the particle by one another. Each and every particles are pushing them one by one. Because of it, the size reduction is taking place. Why they are pushing? Because they are in a fluid which is moving with a high velocity. So we see that we have an equipment called as fluid energy mill, which is used for this purpose, creation of sizes which are very less. So how it is possible, sir? We are going to use 10 atmospheric pressures steam. Steam we are going to use, but its pressure has to 10 atmospheres. So you can imagine how much amount of energy which we are giving for the system for very small reduction in the ratios. Because the only thing is we cannot catch the particle or nip the particle to apply some force on it. That we will see when it comes to us. Then, or intense shear in supporting fluid. So as I said, steam is used. In general, compression is used for coarser reduction of hard solids. So what is the coarser reduction? Yes, what are coarser? Coarser reduction is used for coarser particles. What are coarser particles? Particles whose sizes are measured in millimeters or inches. Now they will be reduced, they will be crushed, and then we are going to get next type of, that is fine particles whose sizes are measured in screen sizes. So how it is possible? We can use coarser equipment or coarser type of size reduction equipment which we are going to use it. Now, impact gives coarse and medium or fine products. Now, attrition yields very fine products from soft, non-abrasive materials. Cutting gives a definite particle size and sometimes definite shape with a few or no fines. Now, here we should understand one more thing. When you are crushing a particle, I said coarser reduction. What is a coarser reduction? First, let us see what is a coarser particle. A coarser particle is a particle whose sizes are measured in millimeters or in inches. Very good. You take a coarser particle, one coarser particle you take, and then you say that its size is 10 inches. One example. Now you hit it. Now when you hit it, what will happen? Is there any guarantee that all the particles are becoming equal sized particles whose diameters are same? It's not at all possible because of only one thing. We are dealing with heterogeneous materials, and in heterogeneous materials, composition of materials will be varying. Composition of the materials along the line of application will be varying. One example I will give you. We have given two particles. There are two particles are there. One particle I gave to an adult and one particle I gave to a small boy. The adult might not have applied the forces, but I told some mechanism. The adult might not have crushed it, but the boy has able to crush it. How? What is the meaning of it? Do you think that the boy will have more energy? No. How he is catching the particle and then breaking it is applied. For example, if I give a cylinder to both the cases, what will happen? I will ask the person to catch the diameter ends and apply the force. It is virtually impossible. You take chalk piece, you take both the ends and you crush it. Is it possible for us? But on the vice versa, if you ask the boy to catch in between and then break it, it will break into pieces. So, boy is breaking, but the adult is not breaking. Means what? What is the orientation of the particle inside the system before breaking is also important. And what is the concentration of the active material in the line of application of the force is also very important. So, since we are dealing with heterogeneous materials, this is a bigger problem for us. In this class, you may not understand it, but when we go to the equipments, we will understand the same concept. Once again, I will explain you, don't bother about it. So these are the some of the ways, that is the coarser particles will be used, and then fine particles impact, and then for example attrition means what? Application of shear forces from soft to non-abrasive materials we can use this. And then why soft materials? Because when you try to hit it or tap it may elongate. So there we should supposed to use the coolant also. You should try, for example, how to cut leather particle. Is it possible for us? So hence what we do, you try to shower liquid nitrogen on the leather particles and it will become brittle in nature, and then we can cut into the pieces. So like that we have some procedures are available for us, we will see in the flow sheet. So like that, but finally the cutting, if you say, it will give definite sizes and shapes. This is the meaning of it. Then principles of comminution. Comminution is nothing but size reduction. It is a generic name or it is synonym of size reduction. Principles of comminution And the criteria of comminution. What is the criteria and how we are going to, what are the expectations for us from the size reduction equipment? Comminution is a generic term for size reduction. Crushers and grinders are the type of comminution equipments. An ideal crusher or a grinder would have large capacity, require a small power input per unit product, and then yield a product of single size or size distribution desired. So these are some of the expectations of size reduction equipment. So as I said just now, comminution is a synonymous for the size reduction equipment. And here we are going to talk about crushers and grinders. So crushers and grinders are the names which are given to coarser reduction only. Remember this. Means what, they cannot do any fine work. So if you want to create minus 200 much, it is not possible. So only in the crushers, coarser reduction only we can use. So hence in some cases they will also call this as primary crushers. So what are the expectations of an ideal crusher? How does an ideal crusher should perform? Then first one, its capacity should be very large. It should be able to do, it should be able to handle more amount of the materials. Very good, no problem. Our productivity increases. Second one, require a small power input per unit product output. So for example, if you are dealing with 100 kgs, then the power consumption should be very less. Then only it is called as a good crusher and ideal crusher. Very good. The third one is what? Yield a product of single size or size reduction distribution required. This point is very, very important because my aim is to produce 1 millimeter particles. I am having 10 centimeter particles. So after the crushing is over, if I get only 1 centimeter particle, then of course the crusher is a beautiful crusher because it is giving only 1 centimeter particle. Suppose if it is giving 1 millimeter particle, it is a useless thing for me. Suppose if it is giving 5 centimeter particle, it is a useless thing for me. Once again I will repeat. I am having a feed of size is 10 centimeters. After crushing is over, I want only 1 centimeter. So if I am having 1 millimeter particle, it is gone. I cannot make it as 1 centimeter. Loss. Suppose if it is 5 centimeter, yes, it has gone through the system, consumed the power, but it could not attain the desired size. So hence an ideal crusher will crush 10 centimeter particles to all 1 centimeter particles only. But dear children, in reality, this is not at all possible because we deal only with what? Heterogeneous materials. So in the heterogeneous materials, the concentration of the active materials in the line of application force is very, sometimes 10 centimeter particle may come out as it is. But in the second orientation, second time when you are putting, it may crush. So hence, this point cannot be satisfied with any of the crusher, but at least we can say one thing, limitation is there. If you use the word, the size distribution desired. So now I will modify my product. It says that, okay, now I will accept the product if it is having a 0.5 centimeters to 2 centimeters. This variation I am going to give. Then I can accept. Then of course we can consider some amount of the profits. Okay. So this is the mini cap. Then the usual method of studying the performance of the process equipment is to set up an ideal operation as a standard, compare the characteristics of the actual equipment with those of the ideal unit, and then account the difference between the two. So this is nothing but calibration which we studied in fluid mechanics. Calibration is a process of conducting an experiment and checking whether the readings given by the system are true or false. Whether they are giving the real values or some values with errors, positive error or negative, that is a different story, is called as calibration. So here what we should do is, first step is what? We are supposed to have an equipment and then you do the process of crushing and then tabulate the readings. Then you go for the commercial one. When the commercial one and then the ideal one which is there in the laboratory, which is giving the same results, then of course we can say, yes, the given instrument, the given equipment can be satisfied. So that is the reason why I said that when a person comes to us, first step is what? In our laboratory, we have n number of experiments, n number of size reduction equipments are there, but which will be used for using compressive forces or impact forces or shear forces or cutting forces. Beyond this, it is not at all possible. So based on this, you try to, we will select one. How we select one? We have to conduct experiment and then we have to tabulate the results, and in which one the losses are minimum, because he's saying 2 centimeters. So I am giving in the range of for 3 centimeters to 1 centimeter. We are having maximum product. Now how do I know? How do I know that we are getting a product in the range of 1 centimeter to 2 centimeters or 3 centimeters? How do I range? Because I have done sieving. Remember. So after crushing is over, we have to do the sieving, which is a very must, which is very important, because when you are not doing sieving, we will not able to identify what are the sizes of the particles and what is their percentages also we are not able to identify. When you are not able to identify, then definitely we are not in a position to judge the performance of the machine. So hence, first step is what? After we are supposed to arbitrarily, we are supposed to select an equipment and do the sieving and then do the differential analysis. And in the differential analysis, if you are satisfied that you are able to produce more amount of particles of desired size, then we select that equipment also. If not, the equipment is rejected. We bring the second. What is second equipment? Second equipment which is used on, which is operating on the mode of the impact. Third experiment may be used by operating on the mode of shear forces. So like that, we select them and then conduct the experiment. So first step is what? We are supposed to conduct experiments, and then in which of the system we are getting maximum amount of Xi. What is Xi? Mass fraction of solids in the given sample. In a particular value, Xi is very high. That indicates that yes, we can go for it. Suppose if the customer wants 1 centimeter, you are having 0.01 millimeter as highest value of Xi. What will happen? The entire material is lost. Because once the particle size is 0.01 millimeters, we cannot get anything. We cannot, because we require 1 centimeter. You got very low size. Now I am not interested in size enlargement. It is a different branch of science. So hence what I should do? I should reject this machine and then bring another machine which gives from 10 centimeters to 1 centimeter maximum percentage without loss. Losses will be there, no problem, but minimize the losses. So this we are supposed to study in our laboratory, and then we should go for the commercial grade, so that the values of the commercial grade, if we are meeting with the tabulated results of the practical one, then of course our experiment is satisfied and the customer will be happy with the machine which we gave to him. That is importance of this paragraph. Yeah, where I am. Yeah. The usual method of studying the performance of the process equipment is to set up. So hence, remember, in our MEO in the lab, every experiment one aim to test the to study the performance of the machine. The aim is only one for all the experiment, to study the performance. We are supposed to pursue the performance. Means what? By studying the performance only, you will understand whether the machine is useful for a given task or not. What is given task? It is written first. I am having granite stones. I have to reduce it to 2 centimeters. I am having ores of bauxite. I should reduce the sizes to 1 millimeter. So first I will write my aim and product result I will write. And now I am going to see which equipment is performing very well for this. So hence in our MEO, in all the experiment, the first aim is only one thing, to test the performance of the given machine. The usual method of studying and performing the process equipment is to set up an idle operation. So in the MEO lab, you should do this first. Idle operation as a standard procedure. So first, how you are adding the material is important, and how you are taking the material is important, and how you are doing the analysis also important. And compare the characteristics of the actual equipment. What is the actual equipment? Once you find that the power consumption is less for the given operation and the losses of the solid particles is not there. Remember, if you get big size particles is the loss, smaller size particles are the loss. But if you say I need 1 centimeter, you have 90% of the solids are converted to 1 centimeter, then your equipment is a good equipment. Remember this. Then compare the characteristics of the actual equipment with those of the idle unit. And the account of the difference between the two is also important. So what is the difference between these two? Because idle one says that it is 98% gain is there, and in reality you have 70%. Then what will happen? We have to go for another test. and then you see that both the results are same, because as I said that in the scale up we have a lot of parameters will be coming to the picture, but the system may be same, but the actual way of performing may little bit different. So how we are going to, what is the concentration of solids which you are going to add, how much amount of time they are taking, all this matters. Okay. When this method is applied to the crushing and grinding equipment, the difference between the ideal and the actual are very great. And despite extensive study, the gaps have not been completely accounted for. See why? Because only one logic. You think that example. I can break the chalk piece, but the orientation is important. If I am catching the chalk piece in between, I can apply less amount of force to break it. I know chalk piece is a brittle material. What is a brittle material? A material which breaks into two halves without giving any signals. Stainless steel rod, if you take it, if you pull it or push it, it gives some elongations are there. Then it starts breaking. But chalk piece is a brittle material. So on the vice versa, at the two ends, if you try to apply the force, even if we ask somebody, Salman Khan also, he cannot do it because it requires more amount of force. But in between, if you apply small, it can break into two parts. With one hand, I can break the chalk piece into two parts. But with same hand, I cannot break if I am catching it. So it all depends upon the orientation, how the particles are entering into the crushing area, how they are cut, and whether they are taking the forces successfully or not is important. Because of only one point, the point is what we are dealing with heterogeneous particles of irregular shapes and sizes. Because of this limitation, we are not able to increase the efficiency of our mechanical unit operation. In my subject, the efficiency is only 55% to 45%. The rest of the things will come out in the form of the heat. Because of only argument. Because we are dealing with heterogeneous materials whose sizes and shapes are very intricate. So definitely after the ore particles are, after blasting of the ore, you get irregular particles only, you don't get regular particles. So for irregular particles, these are the problems which you are going to encounter. So whether you take ideal studies or you take real studies, definitely there will be some gap will be there, and you see that the gap is minimum, and then based on that minimum, you try to suggest that equipment for that gentleman. That is the meaning of it. Beyond this, nothing else. Then, when this method is applied for crushing and grinding, the differences between the ideal and then the actual are very great, despite extensive study gap. This I have studied. On the other hand, useful empirical equations for predicting equipment performance may have been developed from the incomplete theory now in hand. As I said, because we are not, because each and every person will give different types of gaps between ideal and an actual. So hence we have only empirical studies. What are the empirical studies? Empirical equations are those equations which are deduced by conducting the experiments, and based on the graph we have the frames of equation. Y is equal to mx plus c. We know it is a straight line. So first step is what? You try to plot a graph, and based on this graph you try to frame equations, and those equations which are obtained from experimental studies are called as empirical equations. And in my subject there are three empirical equations are there. First one is called as the Retinchen's law, second one is called as the Bond's law, third one is called as the Higgs law. Okay, so in the next class we continue this.